trajectory planning strategy for the links of a walking human-machine system using a neural network. And will be presented by Andrei Malchikov. So please go ahead.
Yes, thank you. You hear me?
Yes.
Can you see my screen?
Yes, you can share.
Okay. Oh, 1 second, please.
Okay, perfect. Yeah.
Hello, my name is Andrey Malchikov, and I want to present results of our investigation, which dedicated of trajectory planning problem for the links of walking human-machine system. The work was carried out in Kursk, in Russia, at the Southwest State University, under the guidance of Professor Sergey Yatsun. Our research team has been dealing with the problem of creating rehabilitation exoskeletons for a long time already. Exoskeletal devices are widely used for rehabilitation of patients with disorders of the musculoskeletal system. The maximum effect is achieved when the patient and the exoskeleton form an integrated human-machine system, the effectiveness of which is determined by the degree of synchronal motion of the elements of this system, including the human and active exoskeleton. When setting the required movements of exercise, executive units of a stationary device, pre-graduated trajectories are often used to provide the required movements signals to the joint, simulating the normal functioning of the patient's limbs. This paper considers a human unit type exoskeleton for lower extremities rehabilitation process. Each leg of the device is composed of 3 links, the thigh, lower leg, and foot. The knee and single-axis hip joint are equipped with a gear motor unit with the rotation angle sensors and the amplifier driver circuit. The ankle joint is equipped with springs which provide the correct orientation of the foot relative to the lower leg of a human-machine system. The scheme of rehabilitation unit equipped with the control system is shown on the slide. The system works as follows. The exoskeleton operator, for example, it's a rehabilitologist, selects the required exercise and its parameters, adjust the size of exoskeleton and its links and its initial position. After that, the patient is placed the exoskeleton and fastened with the use of specialized cuffs. Then the training process starts. The doctor and the patient have the possibility to interrupt the exercise or change its parameters by using a remote control. Then performing a trajectory is important to control the force at the interface point of the operator's body and also as the electromechanical device of the exoskeleton. Another important aspect is to control the person's own muscle activity, as well as the psycho-emotional and physical condition of the patient during training. One of the possible reaction to a change in the patient conditions is related to a decrease in the intensity of movements, decrease in amplitude, and a restriction of force exposure. Or even emergency stop. When working out preset trajectories, making change during the training is a difficult task and can often be solved only at the level of individual control system circuit, for example, in actuator control. Creating a trajectory generator to quickly recalculate the required coordinates for the device drivers depending on the reading of the measure unit system and the operator's commands is a difficult task. The framework of the study introduced a method for obtaining the setting angles for the position control loops of the robot links based on the use of fully connected neural network. The control diagram of the system with the intelligent reference input element is shown on this slide. According to the presented scheme, the supply voltage for the drivers of electromechanical system is formed by a decrease PID controller, the input of which receives the setting value phi with star and data from the magnetic absolute encoders phi with index of actuator I. In our previous work, including paper in Clavar 2020, the choice of parameters for the walking modes of exoskeleton operation has already been explained. The main idea was related to the selection of polynomial piecewise function based on the vector of gate parameters. After determining the time dependence on the coordinates, the inverse kinematics problem was solved. Then the laws of change of the relative rotation angles of the links used as control elements in the exoskeleton control system we obtained. The main disadvantages of this approach is related to the need to completely recalculate the trajectories even this slight change in any parameter, and the inability to change the law of motion during the execution of the walking pattern. In this case, calculation the coefficient of polynomial requires finding inverse matrices, which is required significant computation resources. For an operative intervention in the laws of changing the setting coordinates and quickly recalculate the motion parameters in a wide range of initial parameters, it's proposed to use a trajectory generator based on a difficult natural network. In order to approach the training process of the natural network, a training sample was prepared. The considered input parameters are shown on the slide. The features that the velocity variation during the moment on the maple base occurs due to the scaling factor of the time, adjustable when transmitting the trajectory to the position control loops of the links. And in this case, the time is interval is shown here. When preparing the data, each trajectory contained 10 or 100 points for each interval, and for each other in each of the three step parameters, 100 values were taken within the specified ranges. Those the data base used for training a natural network can be represented by a table with 8 columns and approximately 1,000 rows. All data was randomly divided in 3 groups. The first group is for training, it's 70%. This data is used by the network during training. The second group is validation, 50% of all data. This data is used to evaluate the results of the network and stop training. And testing group, 50%, this data is used to determine the accuracy and performance of the network. The basic networks models used was just a 2-layer feed-forward network trained with the Levenberg-Marquardt method with a number of number of neurons on the hidden layer is 25. Modeling was carried out in MATLAB, and as you can see from the results of training and verification, it took just approximately 200 epochs to train the natural network, and the resulting accuracy according to the test sample was 10 to the minus fifth power. That's enough accuracy for this electromechanical system. For a better understanding in this part of work, a combining graph of the setting angles for a piecewise polynomial trajectory generator and a generator built on the basis of the natural network for left leg of the exoskeleton is shown. As you can see, as can be seen from the simulation results, the use of natural network allows getting the required accuracy with a relative low computing power cost. For example, to obtain 10,000 trajectory points using a natural networks, it takes 0.6 seconds. And the maximum deviation of the accuracy is less than 1% of the amplitude of the movements and satisfies the requirement of the task. Modeling the operation of trajectory planner based on the use of fully connected natural network showed satisfied accuracy and speed of the method. At the time of this paper writing, we only planned to use it on real prototype exoskeletons, but now this described trajectory generator, trajectory planner has already been successfully implemented in the form of software on the doctor computer and is undergoing the following stages of research. We will definitely tell you about the results of these experiments of its test in our next papers. Thank you so much for attention.
Okay, thank you, Andrei, for your presentation. Is there any question from the audience? No questions? Okay, I have one question. Well, did you compare your gate generator with another type of generators? There are a lot of gate generators already addressed. Have you ever tried to use another different gate generator?
Thank you for the questions. In this paper, we show the compare with our own trajectory generator, but we use a different generator for compare. And neural network, it's good to use, and it's important to know that if you want to consider more parameters for trajectory generator, not only shown on the slide, we need to do a lot of calculation. But main idea of our idea is that we want to generate relies on the microcontroller, and a lot of calculation. It's not good for microcontroller or onboard PC. And when we use natural network, the main problem is to train that. But when we have already trained natural network, we have no problem with the ready-made trajectories, maybe from experiments when we have no analytical function for this. We have only a ready-made graph, for example, and we train natural network, and it works in our electromechanical system.
Okay, thank you for your answer. I think there is a question, so please, Daisuk.
Yes, thank you very much for your presentation. I have a simple question. How are differences in the body size considered? Because user has a different body size.
Mhm. Okay, thank you for the question. If I correctly understand, you speak, I answer about how many parameters we used in our trajectory, yes? All parameters for this paper are shown on this slide. We have no link range, which dependence of the human body size. But it's important things, and it's when we calculate our trajectory, we use the parameter of body. It's mostly length of links.
Thank you very much. I just think that the range of the motion of the joints will be different in the different people, I think. So I have I think simply and one trajectory cannot fit the every people, I think. No, it's very simple.
Okay. I agree. Yes.
But time is up, so thank you very much.
Thank you.
Okay. Thank you both. Thank you, Andrei, for your presentation.